So I'm just 10 minutes earlier than the previous recorded time so that I can check whether the quality of sound and image are good for transmission. So I'm just testing the microphone once again to check if the sound is going good. Please do tell me if something is going is going wrong with the image or sound quality, please. So I'm just waiting for the actual time, 11 a.m. in the Brazilian time zone, 2 p.m. GMT, and 4 p.m. Berlin local time, so that we can begin the presentation. Hello everyone. I think it's time already. I'm trying to be as punctual as possible. We're going to begin this presentation about SimPatico. It's a simulator for the analysis of TDOA methods. First of all, I have to do some acknowledgements. First, that the present work was based on my bachelor thesis for the electrical engineering course at the Federal University of Rio Grande do Norte. I am very thankful for the help and support of my supervisors, which are Professor Dr. Vicente Souza and Dr. Danilo. I don't think that I could even have joined the GPP Com Research Group at the university if it wasn't for them. And I'm also very grateful for all the support that they have given to me during all these months that we took to build the simulator. So, to begin with I'm going to go through a brief summary um, of the content that I'm going to present here. First of all, I'm going to talk about what is TDOA, in what kind of situation do we use it, the applications that are involved with um, with the calculation of TDOA, pros and cons. Then I'm going to go through the mathematical um, formulation of the problem, how we can address some of the issues that we get from environmental conditions as well. And afterwards, I'm going to talk about the channel modeling, which is the distortions that we're going to apply over the signals, noise and reverberation. And then I'm going to expose some of the functionalities of the simulator. This is actually not very common to do, explain some code and afterwards, but the thing is that after SimPatico is released, if somebody wants to take a quick look at how some of the functions work, he or she will be able to do so in a quite quick fashion. After that, I'm going to show some of the outputs that we can have with SimPatico, what kind of uses we have for it, and some of the we're going to analyze some results that we got, some theoretical analysis. In the end, for the conclusion, I'm going to give some final remarks and give a brief. We're going to take a quick look at some further eventual future work. Right. So first of all, what is TDOA? So this is an acronym for time distance of arrival between some signal coming from a source and that's traveling towards a set of sensors. This is more commonly used in localization techniques, and that can happen in a lot of situations. For instance, we can have device positioning in 5G, vehicle positioning such as cars or submarines. Speech source localization is also very common when we work with TDOA because um, in many situations we work with acoustic signals and our array of sensors are is actually just a set of microphones. But some other interesting applications are also included in this research field, such as power line fault localization. Why is this entity so important? Because beginning from the time difference of arrival, we can actually estimate the angle of arrival from some signal, right? There are some positive and negative aspects about TDOA. So one of the things is that we don't have to synchronize the clocks between the sensors and the source. So that's actually a very nice thing. We don't have to be that worried about the source signal. Another thing is that we can apply some statistical methods that are widely known, such as maximum likelihood estimation techniques. We can easily talk about Cramer lower bound, and I'm going to explain some of that later on. And that's really, really interesting in this scenario. However, the clocks between the sensors have to be synchronized. Um, and a big problem can be the cross correlation calculation. Why is this important? Why did I highlight it with a red color? So the major problems are there is it's really recurrent that we have reverberation and noise over the signal. So what is the principle behind the cross correlation here? So if we have a setup with only two sensors, which is really common actually, if we have these two sensors, we calculate the cross correlation between the incoming signals in each sensor, and then we check where the global peak of the function happen in the time domain, and that's going to correspond to the time difference of arrival. However, because of these environmental effects, this peak may not be unique. This peak may be really close to other peaks, so this makes the this ingenuous approach really really difficult to realize. And we can address that. For now, I'm going to talk about some of the TDOA principles. We're going to see here that there is a way to address this thing, and also you're going to see that there is another way to calculate the time difference of arrival. But first, I cannot go any further if I don't talk about the signal model. So as we can see in here, the received signal model is just a scaled version of the source signal, which is delayed, and then it is summed to the distortion components. For instance, I expose here the noise. And this delay, the tau I that is highlighted here, is the thing that we're looking for in this scenario, right? So first things first, I talked about in the first place about the generalized cross correlation (GCC). Um, Here, our setup is going to be made of only two sensors, and it's way more useful if we talk about the GCC in the frequency domain. So in the frequency domain, the cross correlation operation is just it's quite simple in the frequency domain. Just multiply the first signal by the complex conjugate of the second signal, and that's the cross correlation. What happens will correspond to the TDOA, right? So the weighting functions. As we can see here, there are six weighting functions here, but there are actually more in the literature. But I'm not going to go too much deeper on that because it would be really difficult to analyze lots of weighting functions just at once. So first of all, we have the Roth filter. It has a rather simple formulation, but it has a rather simple formulation for the Roth filter. It um, is it okay? Is it transmission? Is it transmission going back? Is everything okay? I've seen that some people said the transmission has had a little crash. Is everything okay? Please do answer me if everything is back. I unfortunately my internet provider is not that good, so I deeply apologize for that. All right, so thanks for the answer. The internet is back. So I was talking about the Roth filter. So it has a quite simple implementation. We just need one signal, and we take its complex conjugate. Right. So what is its main property? So this filter suppresses frequency regions where the result of the correlation process may possess significant error. So this thing here can be quite useful when we um, when we are dealing with some high frequency components. That's really interesting. The following, we have the Scott filter that actually accounts for smoothed coherent transform. And it can be seen as a pre-whitening filter with a cross-correlation operation in the sequence. And it leads to superior performance in the case of low noise level. Um, we can see that there is a cross-correlation involved here because we have the first signal multiplied by the complex conjugate of the next one, and that also happens when we change the signal. So you may have some interesting results as well. The next filter, this is going to be particularly important in the following. I'm going to address that again. So, um, so FAT actually means phase transform, and it makes the cross correlation operation only dependent on the channel responses. So we have only the information about the phase of the signals, because after all we are taking the cross correlation and then we are dividing it by the absolute value of the whole process. Right, so the next filter is the first one where we have um, noise components on the weighting function. It's represented by the S here in the formulation, and actually this is one of the methods that have one of the best performance. We're going to see that later. Right, so why does it have this behavior? So it maximizes the deflection criterion, which is the ratio of change in mean correlation output due to the signal of interest compared to the component of noise only. This is a rather complicated concept, but um, but it will be really useful in the further analysis that we are going to conduct. So afterwards, we have some considerations um, about Cameral lower bound. So here in the formulation for the MLE, maximum likelihood estimator, we have this function gamma. That actually means the Wiener Hopf optimum filter, and this is a rather important piece of this filter because it makes the filter reach the minimum possible variance for an unbiased estimator, which is also known as the Cameral lower bound, or CRLB in the literature. However, there's something that's not really great about it. The signal should not be affected by reverberation. The delay has to be constant, and the signal should be described as stationary processes. So it has um, it has some limitation on its use. However, to address this issue, there is a modified maximum likelihood estimator filter, which is also implemented in SimPatico, and it aims to achieve optimal performance in noisy and reverberant scenarios. This is reached because the formulation addresses some signal properties, such as the variance of the angle of arrival and the cross-spectrum phase. We're going to see how each of these filters behave in different scenarios later on. So the other method that we can use to calculate the time difference of arrival is the stereo response power. The FAT here in the name. In the situation, we can use more than two sensors, but for each of them, for each correlation process, that right. So I've seen that it has been cut out again. Um, I deeply apologize for that again. Is everything okay? Please do tell me if the if the connection has gone back to normal. I'm just waiting for everybody, for someone to respond. Is it back already? Okay, good. Thanks. All right. So we're just going to apply the GCC FAT for each pair of sums. We're going to sum that up, and in each of these sums, we're going to multiply it by an exponential j omega tau. This tau here is actually the time that it takes for the signal to travel to the other sensor. So we have to need some information about the speed of propagation and the distance between the sensors. We can see here right on that in non-reverberant environments, the SRP FET and the GCC FET have similar performance when we have only two sensors. But when we have more sensors, the length of the signal gets bigger. We have more information, and so the performance of this process overall gets better and better. Right. So following, we're going to talk about the channel modeling. Um, because the environment is not a perfect place, we need to address some situations. We need to address some deterioration that can happen over the source signal. We're going to talk about noise and reverberation, and how we have applied these entities over the source signal. So the first one we're going to talk about is just the traditional additive white Gaussian noise, which it's pretty common in telecommunications. Its formulation can be seen here. That's the probability density function, or PDF for short. And it's the models that I talked about. They were designed considering this noise affecting the signal only. So yeah, that's pretty much it. Let's move on. So the simulator also has some non Gaussian noise model noises, because it is important to see that in many applications the Gaussian modeled noise is not very useful to model impulsive noises and some other higher frequency noises. So we had to implement some non-Gaussian noise models. The first one here that I'm going to expose is the Gaussian mixture model, which is a linear combination of Gaussian PDFs. As you can see here in the formulation, is just a scaled version of Gaussian PDFs. The scaling factor here, Ci, because of we're talking about linear combination, the sum of all scaling factors has to be 1. In the simulator, we have implemented the mixture of two Gaussian functions only. The variance of the first one accounts for the contribution of a purely Gaussian noise, where sigma 1 accounts for the variance of the first Gaussian function. Well, we can also talk about standard deviation on that sense, but here we are worried about the variance. Anyway, the sigma total here is the variance of the whole distribution, and C1 and C2 are the weights of both Gaussian distributions. The variance of the second distribution is just a scaled version of the first one. So sigma 2 is actually just equal to rho times sigma 1. But what is this um, rho factor? It describes the impulsiveness. We are worried about modeling impulsive noises in SimPatico, because it's quite common in some in acoustic signal. So this thing here, rho, is going to address this thing, and it's going to be a really important factor in our future simulations. The other model for the non-Gaussian noise PDS the symmetric alpha stable model, S alpha S for short. It is more useful to describe impulsive noises. That's a rather common that's a rather um, common thing to see in the application. It's also present in the literature that there's a more used method to model to model impulsive noises. So I'm not going to go too deep on its mathematical formulation because there is not actually a closed form of the PDF for this model. So I'm just going to talk about some of the main parameters that are involved with this model. So it has four main parameters: the index of stability alpha that can vary from 0 to 2. You have the scaling parameter sigma, skewness parameter that can go from -1 to 1, the shift parameter mu. Um, alpha and alpha and beta they can be set by the user in the simulator. So why is alpha important? When alpha is closer to 2, we have a more Gaussian-like probability density function. And when it gets closer to 1, it assumes a Cauchy-like form. What is the scale parameter actually? So it will correspond. So if we imagine that we have a Gaussian PDF with alpha with the value of 2, the scale parameter is going to correspond to the standard deviation, and mu is going to be the mean. So if alpha is something in between 1 and 2, these things will have some statistical meaning, and the noise is going to behave in a different fashion, and it's going to be really interesting to see how the methods behave in this strange area, I would say. The important thing here is that in the case of S alpha S, the model imposes beta equal to 0 and mu equal to 0. The parameters, as I said before, alpha and sigma are going to be configurable by the user to determine a specific geometric signal-to-noise ratio. I'm going to explain this concept a little later. Impulsiveness degree. This parameter will then account for the severeness of the noise in the simulator. So the last channel modeling factor that I'm going to talk about here is the reverberation. It also has a very complicated and deep mathematical background behind it, so I'm not going to be too specific about the math behind it. But I have to say here is that the reverberation scheme that you use here follows the plate class topology and allows for custom values of pre-delay and sampling rate. There are some few steps involved with the reverberation model. First, we have the precondition of the input by applying just a pre-delay and a simple low-pass filter of -3 dB cutoff frequency. It's just a single pole that's just to suppress higher frequency components that are not desirable for reverberation. Right, so we apply some decorrelation with 4 all-pass filters in series, and then we feed that into a tank processing block so that we can simulate the decay of the amplitude of the reverberating signal. In many situations, the decay has an exponential-like shape, and that's kind of what we see pretty often in acoustic applications. Right. So following, I'm going to talk about the simulator itself. But first of all, I have to talk about like why have we actually built SimPatico? I mean, we have so many issues involved with the localization schemes, but there might be some other simulators in literature. However, um, I mean, there are actually some other open source simulators, but they are limited in some to some extent. Sometimes they only gather information from GPS via Wi-Fi and the received signal strength indicator. So sometimes that's information that we cannot get. Some other simulators are based on time of flight, but they are not. They do not allow us to evaluate the performance of TDOA methods in more than one performance metric. So the main contributions are that we provide an open source simulation tool, which is named SimPatico, which is just an acronym for Simulation Platform for Position Location. That was a pretty creative name. So that we can give some help in the conception and evaluation phase of TDOA methods. We also provide an unified simulation platform to benchmark lots to benchmark all these several TDOA methods, so we can check whether whether some method converges faster to close to zero round mean squared error. Also by means of probability of resolution. I'm going to address that later. We also provide a um, unified simulation platform to test these algorithms in different impairment models, including Gaussian and non-Gaussian model noises, and also with reverberation effects. That's not something that we haven't found in the literature. We also provide implementation of several TDOA and DOA methods with user-friendly configuration platform. DOA actually means direction of arrival, so in SimPatico, we also have classical implementations of esprit and music algorithms. I'm not going to talk about them here, it's not the main purpose of this presentation, but they are also present there. And we also give many performance comparison examples, including aspects of including many performance metrics. We can see the performance of the TDOA methods by by the round mean squared error, probability of resolution, absolute error, and mean of the calculated angles. Right. So I'm just going to talk about a little about the execution flow. So first of all, um, we begin with configuring the setup parameters. Actually, first, the simulation campaigns are composed of parameter files, which contain parameters about the source signal, number of sensors, the distance between them, and other relevant information about the simulation itself. For example, here we can set up the algorithms we want to use, the type of signal. That can be a gong, signal, chirps, just a sine wave. It can also be an audio file given by the user, for instance. We can configure the distance between the source signal and the sensors, the distance between the sensors, source frequency, sampling frequency, number of iterations, speed propagation, noise channel, and so on. There are many things that you can work with. After that, we check data. We have to see if all parameters pass into the structure, make the code reusable and maintainable. These parameters are then analyzed to ensure that they are consistent. So, for instance, the distance between the signals may not be higher than the wavelength, for instance. That would not allow us to carry a simulation. And then we create the signal itself. It is created based on the type of the source signal we want to work with, the type of signal I expose. These signals actually are also available in real and complex forms, and that's basically it. That's where we're going to apply the distortion effects over the signals as well, right? So then we evaluate the algorithms. The simulation is executed in snapshots, so we sample the source signal. The angle of arrival is estimated through the chosen TDOA methods and figures of merit. And the execution of this snapshot is held for all ranges of SNR, number of iterations, Monte Carlo runs, number of samples, and so on. The angle of arrival is estimated with basis on the chosen TDOA algorithms, just to complete it. And afterwards, with the results we got from these evaluations, all the results are stored into a structure. They're saved into an output file. All the performance metrics are then plotted and saved for further analysis. And the paths for the output files are automatically generated. Um, Here we have just a diagram for the execution of the code. First, we set up the parameters for the campaign. We check if they are consistent. We create the signal alongside noise and channel models. We evaluate all the scenario conditions. That's why we execute the snapshots. Then we evaluate them by bringing them to. We get all the results. We plot them, and in the end, we get the results from the analysis. Right. So following, as I said before, I am going to go through a little of the code. This is not very usual, but if somebody in the future wants to take a quick look, just want to do some recap over the some of the functions, he or she can refer to this presentation and look up at this slide. So first of all, we have the algorithms folder. It contains the TDOA and DOA estimation methods for the user-defined setup. They include all the formulations that I talked about earlier, GCC and SRP methods, and eigenvector-based techniques. The inputs for each of them depend on the desired source signal, which can be, for example, the analyzed signal itself, the sampling frequency, the distance between them, and noise components, and so on. The respective output is just a calculated angle of arrival. Right? So following, we have auxiliary codes, which has some really crucial functionalities of the simulator. One of them is just the create signal function, which synthesizes the source signal. The available options are the ones that I talked about earlier, like Z of choose sequences, random sequences, sine waves, laughter, chirp, gong signals, and so on. The other very important function here is snapshots. Here, the angles are calculated via the chosen methods and the performance metrics that are determined by the user. In distortion models here, that's where we find the noise and reverberation models that I talked about earlier. You can choose whether or not you want to have only real Gaussian noise, complex Gaussian noise with reverberation or not. Also the alpha stable model noises as well. Right. So in campaigns, that's actually in the simulations folder. The user can specify a set of simulations by choosing the parameters and scenario he wants to build. The simulation produces all results it stores all results in the results folder with all data files and plots. The performance metrics are provided based on the dependent variable that can be the SNR, GSNR, number of sensors, and length of the source signal. Right, so now we get to the use case. That's where I'm going to expose some of the results that we can achieve with SimPatico. The first setup here we're going to use is just we're going just to use one of the most basic setup that we can have is a gong source signal. We have only two sensors that are just 0.2427 meters away from each other. The sampling frequency is around 8.2 kilohertz. The SNR was set from -20 up to 40 dB. We have 1,000 Monte Carlo runs and 1,000 samples in each of them. There is no reverberation, and we have only real Gaussian noise. Right, so we're going to compare all the all the TDOA methods by means of round mean squared error and the probability of resolution, or PR for short. Um, Here, so we actually get some interesting results, some expected results already. As expected, the Eckhart, the ML, and the modified ML filters are superior than the others in terms of behavior. They converge to zero round mean squared error much quicker than the other filters. That can also be seen because it's also seen in the probability of resolution. It reaches PR close to 1 in a much steeper fashion. That's, I mean, that was expected because these filters should provide optimal solution, and they have very similar behavior. They are MLE methods, right? So the other classical filters obtain the expected performance by reaching high PR only at higher SNR values, and the GCC route is the one that has the worst behavior of them all. But it's going to be really interesting in other analysis that we're going to conduct here. We're going to compare them in non-Gaussian model noises. This is really interesting because it's a comparison that is not available in the literature. So it's going to be interesting to see how these algorithms behave in under non-ideal conditions. But we have the same setup, only two sensors, but the source signal is going to be affected by GMM noise. Actually, if you keep the source signal, it's going to be the gong signal, but because of the nature of this noise, we don't have actually a defined variance. So we have to introduce the geometric signal to noise ratio concept. It is used in S alpha S processes, and it's given and it's calculated by this expression where CG is just the normalization constant. It corresponds to an exponential, and it's close to 1.78, so that we ensure that the GSNR corresponds to SNR when the channel is Gaussian. S0 is the geometric power of the S of S random variable, and A is the root mean square value of the signal. It's not actually the signal amplitude, but it accounts for that. So it can be a little misleading, but that's the simplest way I could put it. Right. So once again, we see the results in with respect to the GSNR. Here we see that the filters that have the best performance are the same when compared to the previous analysis, but they behave in a different fashion. The descent is much steeper. It happens much quicker for all the methods, but as you can see here, some of the performance actually there's actually some deterioration on the performance um, because the descent or ascent in the PR just happens in a considerably higher GSNR. So, for instance, we have all the other methods outside the best ones, and GCC route, they just appear to converge in GSNR close to 25 or something. So that's some of the some of the conclusions we get. This is interesting because this is actually a highly impulsive channel. The rho here is close to 1,000, so that's pretty high already. And the last noise analysis we're going to conduct here is the S alpha S. So here we have again the same setup, the same source signal, but it is going to be affected by a different noise model. Here we have two values for alpha that we're going to analyze: 1.7 and 1.3. 1.7 is already is already pretty impulsive. Makes it a really impulsive noise. But 1.3 is a more extreme case, and then we're going to see how that affects the performance overall. Right. So as we can see here, the probability of resolution in RMSE are deeply affected because of the impulsiveness of the noise. Again, the filters that behave the best are the same ones. It's going to be the ML, modified ML, and Eckhart. Um, and the probability of resolution of the other filters is moved further away. But in this case, where we have alpha equals 1.3, that's way more extreme. I just couldn't find a GSNR that could fit probability of resolution close to 0.9 for all the other filters, and still the maximum likelihood filters they converge in only a much higher GSNR, like close to 30. So that makes it makes clear that we need to develop um, this kind of filters for impulsive noises. It can be seen here. It's pretty clear that these things here may not be very useful when we talk about impulsive noises. So now we're going to talk about resolution analysis. So our horizontal axis here is going to be the number of samples we get. We still have only two sensors. Now we're going to go back to real Gaussian noise, and we're going to see the round mean squared error for SNR equals to 3 dB, and then we're going to see how dependent these filters are on the number of samples. Um, the first thing we can see here is that for the SNR equals to 3 dB, how precise is a filter by means of the number of samples. So we can see here that actually the AML filter is not that good when we deal with a smaller number of samples. That means that it's highly dependable on the number of snapshots we take, and the GCC Roth actually that had the worst performance in all the analysis we conducted earlier. He actually has a pretty much has a considerably better behavior because it converges much faster, so it's not that dependent on the number of snapshots. Following the Eckhart filter and the GCC FET also to have this better behavior. Right, now we're going to conduct the reverberation analysis. So I believe I said earlier that these filters were not designed to reverberating environments, but um, but the SRP FAT actually has a really interesting property. It can be used in this kind of scenario because of the explanation we get in the end that addresses some issues, some reverberation issues, and it's also we can see that as the beam forming process. So it's really interesting. We're going just to compare the GCC FAT and the SRP FAT with two sensors with a pre-delay of 0.1 seconds. And we can see here that the difference is pretty considerable. The only two sensors we have a method that converges and another method that does not converge. So it is a major result we got from comparing GCC and SRP. The last analysis we're going to conduct here is just the number of sensors for SRP FAT. So we can see that SRP FAT can be really useful in a number of situations, but how do things get better when I increase the number of sensors? Um, we're going to conduct here analysis with only real Gaussian noise as well, and we increase the number of sensors from 2 up to 8. And we can see here that the curve gets relocated to the left more and more. So we can see that the improvement of behavior is quite visible. The more we get, the more we get sensors. When the number of sensors is closer to 6, 7, or 8, this actually gets a maximum likelihood like performance. So that's really great. If we have an application that can have more sensors, that's something you need to consider, because you have more snapshots, length of the signal gets higher. You have more information about the signal, so this is really interesting. This is quite common in applications where we have microphones for analysis of acoustic signals. So jump into the conclusions. We get some final remarks here. So SimPatico was developed as a much needed open source evaluation tool for this kind of analysis. This is something we are really proud of. It was kind of tough work during the second semester and the first semester of this year. Um, it's also the access of unified platform to analyze, develop exist or new strategies is a beneficial contribution to those interested in these assessments. We also implemented more ideal environmental conditions so that we can analyze more realistic situations. That's one of the biggest contributions of Simpatico. There's also a very wide variety of TDOA algorithms. They can be a benchmark for different projects, and they can be evaluated in a number of performance metrics. The development and evaluation of robust methods can also be done with Simpatico. You can also implement some other filter you found, or some other eigenvector-based technique that the user wants to. And so I leave a suggestion here for future work, is that we need other MLE estimation methods in case it can be implemented. So you can evaluate that with the noise and reverberation models that are available in Simpatico, and that leaves an open branch for further studies. I am really thankful for everybody for taking your time for watching this presentation. I hope it was a good one. I also hope everybody's doing well during the quarantine. And now I'm going to leave some space for questions. I'm going to check all the questions you have. Um, you have to know that there is some delay between my speech and what you're seeing, what you're writing as well. So I apologize if it takes a little while for me to see it, but feel free to ask some questions and discuss some things. So there's a question here. I would like to ask you if you think of expanding it to RF signals instead of acoustic. Well, we can use that, but we did not have any RF signals implemented in Simpatico. If you have a measurement, like if we gather some data for a radar or some other antenna, it could be surely evaluated here. That's a very nice suggestion. We could, yes. So my answer is yes. We could expand it to RF signals. That's a suggestion that has appeared already. So yeah, we think about it. This is made it interesting because we can use the SRP factor instance in many situations, like radar applications. We work with the beamforming process, so that can be really interesting. That's a really nice suggestion. So just keep waiting for some other questions. So does anybody have any more questions? I'm open to any discussions you want to carry here. Otherwise, anyway, you can all of you can reach me afterwards. You can send me a message. And so my last words are thank you very much for taking your time. It was almost an hour long presentation. Please stay safe, stay at home, and stay healthy during the pandemic. So thank you very much for your time, and I'll see you guys next time.